So we've now finished part 2 of the sequence of lectures, and we're moving to part 3. So part 2 was a number of topics which general topics that always crop up in some form or other, that you have to have a discretization, you have to think about time stepping, and there was this linear algebra problem. Remind you must not code anything you saw. Okay, so in the specialized topics, these are topics which will occur. There are several topics, and perhaps only one of them is relevant to you. Hopefully one is relevant to you. It's most unlikely that all of them are going to be relevant to your interests. So they're specialized topics. And the first one I'm going to deal with is hyperbolic equations. The Navier-Stokes equations is partly diffusive with del squared u. It's partly hyperbolic with u dot grad u. So we're going to talk about the hyperbolic equations. This gets particularly difficult when you move to high-speed compressible flows, where the wave equation is a hyperbolic equation. So the first thing to say is don't do it. That it is a terrible mess. You'll see that nothing works. So it should be avoided if it's purely advection. Advection plus something you can get away with. So advection plus diffusion, lots of diffusion, it's quite safe. Advection plus chemical reactions, again that's quite safe. Advection plus diffusion, advection plus reaction is going somewhere, definite. Advection on its own is really boring. You just take the initial state and you move it sideways. Keep on moving it sideways. That's very dangerous that nothing's happening, because any error will sort of just add on. If you've got advection going sideways and diffusion, then it's in a nice balance and any little error will correct itself by the diffusion switching in. So advection, diffusion, of course you've got to be careful. You have to make sure the step size is small enough to resolve the diffusion boundary layer. So that would be the Reynolds number based on the grid size, the Peckley number based on the grid size has to be less than 1. In other words, U times delta X divided by the diffusivity D has to be less than 1 in order that you can resolve the diffusive boundary layer. You also have a criterion that we've had before. The delta T has to be less than delta X squared, with the dimensional form is the diffusivity times delta T has to be less than delta X squared. Those two things, those two conditions give you the CFL condition, that the time step times the speed, how far you travel in one time step, is less than the grid size. So these two conditions imply that. In the case of advection plus reaction, you need to be able to, you mustn't move further in a reaction time than one grid block. So if tau is the reaction time, then this u tau is how far you can move in one reaction time, and delta X has to be less than that. And then plus the CFL condition tells you that the time step, pretty obviously, better be smaller than the reaction time. So they all fit. There's two constraints, and the third one is automatically satisfied. Whichever two you take, the third one will be automatically satisfied. Okay, so that's advection and diffusion is okay. Advection and reaction is okay. Pure advection on its own has problems, and there's essentially two problems. One is you just advection is moves this information sideways without changing it, please. And that means if you make a little error, I'm going to move the error sideways. And I make another little error, and by time 1, the solution is dominated by the errors. You just accumulate errors. It would be nice if the errors were randomly accumulated so that they began to cancel out with one another, but it doesn't work like that. The errors just accumulate on you. The other thing is, with purely and moving things sideways, you can produce shock waves. You might have some information here which is traveling fast and some information here which is traveling slow, and this will overtake and you get a breaking wave. You get a shock wave. Shock waves, discontinuities, are a bad idea for numerics. You'll find that you want a high order accurate method to get rid of some of the accumulation of errors, but then a high order method assumes the solution is smooth. If the solution has got a discontinuity, it blows up badly. We'll see that. There's also things called rarefaction waves, if you've done that. And these are just bad for you. Okay, so there's a big hint here. Get out of this difficulty is to reformulate the question, reformulate the governing equation in Lagrangian coordinates, where the coordinates themselves are moving with the flow, so you don't have to compute anything being handed over from one grid block to another. You just sit on a grid block. The grid block does the moving for you, so you just carry the information and it is safely transported. Okay, I've split this very long lecture into two halves. The first half will be about advection, very simple advection, of smooth information, smooth data. The next lecture will be about advection of discontinuous data, or shock waves, in other words. So we're going to have smooth data to start with. I've got here an expression x minus 1 squared and 2 minus x squared. This means that the data is 0, and then it comes quadratically up to a maximum of value of 1. And it's quadratically down to 0. So it goes nicely to 0. The function and its derivative are 0 at the join with 0 data and non-zero data. I'm going to satisfy the advection equation, just move sideways at velocity c, and we'll take c to be a positive constant. So we're just moving information sideways, and we still have problems with that very simple problem, with that very smooth data. I'm going to present 6 different algorithms, and none of them are good. They get better, but then none of them have the word good. It's quite easy to generalize this to where the velocity c is a function of position, where the velocity c is a function of position, and say the solution u. And we can even go over to vectors u and vectors x. The methods immediately move sideways. I'm going to talk in terms of finite differencing. The way that you can master these hyperbolic equations is to couple the discretization in time and the discretization in space. If you use finite elements, you're stuck. You've discretized in space and you can't couple in the discretization in time. Equally spectral methods. So with finite differences, you have an advantage that you can couple in what you're doing in space discretization and time and somehow do better in doing the two together. There's a standard notation. I use a superscript for time level n. I'm having equisized time steps and equisized space steps, and I've got a subscript ijk, in this case L, for the space location. Okay, the simplest thing you'd like to do is totally unstable. You can see it blows up. So this is centrally differenced in space. So for the point L, I consider L plus 1 and L minus 1. We like central differencing. And then it's forward time stepping in time in order to be an implicit system. So we go from n to n plus 1 divided by delta t. In other words, I've got a numerical molecule. The curiosity in this subject is we plot x sideways and time upwards. So I've got my point, time level n, position L, a space advance, a space with the point behind, and then going up to time level n plus 1. That's my little numerical molecule written in that form. And I'm showing here solutions at every time advance, real-time advances by 0.2 with a delta x of c, delta x of 1/20th and c delta t of 1/80th. And it's unstable. And it can't be made stable by any choice of delta t. So all the way along, we're going to have to look at the 6 different routines to find out, are they stable? How do you find out whether they're stable? And there's a standard method, and I'm showing you the details for one and then the results for all the other ones. What you do is you substitute effectively a Fourier wave. You say that the space dependence, L, is an e to the I x, kx, and then the amplitude at each time level advances by the same factor, a. So we start with a, then we have a squared, a cubed as we go from time 1, 2, 3. And what we put this Fourier wave into the algorithm, and we try to find out how does a depend on k, and it's stable if the size of a is less than 1. If the size of a is bigger than 1, it's going to grow in magnitude as we take subsequent time steps. Okay, so you shove this into the algorithm and you find that a is 1 minus I mu sine theta. So we have a crisis in this, a notational crisis. The people who study these equations use mu for c delta t divided by x. In fluid mechanics, we use mu for the viscosity. And you just, for 2 lectures, live with the fact that there's no viscosity because it's a hyperbolic equation. So mu is available to be used as the CFL Courant-Friedrich-Louis parameter. This dates back to 1928, I think, as the size, non-dimensional size of the time step. So we have this expression that a is 1 minus I times the sine or the size of the time step, and then theta is how does this Fourier wave change over 1 delta x. So, and it's sine theta, and then the magnitude of this is always 1 plus mu squared sine squared, because it's real plus imaginary, real part squared plus imaginary part squared, all square root, and therefore the size is always bigger than 1. And therefore it's always unstable. Okay. We needn't worry about the shortest wave. Okay, so the next algorithm fixes this, and so in the time step, it doesn't use the information. It doesn't step from time level n to n plus 1 by going from here to here, but it takes the average of those two. That's averaging smooths things out. So we average those 2 values there to use for the value there, and then we step forward from the average of those 2 up to there. So that gives me an algorithm which can be written like this, that time level n plus 1 is time level n, and using the information at L plus 1 and the information at L minus 1. Right? So you go and do your stability analysis again, and you find in this case A is cos theta minus I mu. So we have the same minus I mu sine theta, but we have a cos theta rather than a 1. And that's good because the size of A, the size of this complex number, is cos square root of cos squared plus mu squared sine squared. And that is less than 1 for all values of theta. So for all, I was putting in 1 Fourier wave, but I'd like this to be stable for all possible Fourier waves, so all possible k's, so therefore all possible thetas. It's stable for all possible thetas as long as mu is less than 1. Then it's less than cos squared plus sine squared. So this says in the CFL parameter, we mustn't propagate information in 1 time step further than 1 grid bolt. So this is the result. It's super stable. So here I've put the CFL parameter equal to 1.1. It's supposed to be less than 1, and it blows up. So it's true that if you give it an unstable value, it will blow up. But if I put the parameter equal to 0.5, it's stable. Unfortunately, it's too stable. The solution is just decaying on me. The amplitude's going down and it's spreading out. By this is when we get to time 1, it is down at some 60% of the original value. So very quickly, it's gone. Your solution has gone away. So this is too stable, this method. We'd like to understand how this stability, okay, we've first understood the stability. Now we'd like to understand this damping. Where do we get this damping from? How big is it? Can we understand that? And to do that, we use, for all of the algorithms, I'm going to do this, we look at the long wave error analysis. So for long waves rather than short waves, the instabilities, the stability analysis tends to be all about short waves. This damping tends to be about the long wave behavior. For long wave behavior, the function doesn't vary fast between one grid point and another grid point. It varies rather slowly. And therefore, I can make a Taylor series expansion. So the value of the function at L plus 1 is the value at L plus the derivative, there's an x derivative, plus half delta x squared, 2 derivatives. Equally, the value at time level n plus 1 is the time value at n plus delta t times the time derivative plus a half delta t squared times the time derivative. So I then throw that into this algorithm, the expressions for L plus 1, L minus 1, and n plus 1. To first order, I get exactly what we should have, that ut plus cux is equal to 0, but then I look around to see what else I've got. I have ut is equal to minus cux, and then I have a delta x delta t squared sort of activity here, and you can see that there's a uxx. So the correction term in this long wave analysis is a diffusion behavior. And we have an expression for the diffusivity, and it has a very alarming feature that if you decrease the time step, the diffusivity gets bigger. So if you stare at this graph, there's 2 lots of graphs, and the smaller one has, which is the dashed curves, has a time step which is half that of the continuous curves. So this algorithm damps faster if you have a smaller time step. This is not very good. Okay, so 2 algorithms are not good. Third algorithm. Well, you will have known from the discussion about finite elements that if we're propagating information sideways, it's rather bad to use information of where you're going to work out how to get there. It's counter to the physics in the governing equation. So in upwinding, we'll just use information upstream, not use the downstream information. So here I've got forward time stepping in time as before, and first order, it's backward differencing, first order differencing from where I've come to in the past. So it's only first order accurate. We go away and do the stability analysis, and you can find that the stability criterion is a squared is 1 minus some expression sine squared theta, and that a is less than 1 in size for all values of mu, for all values of theta, and for all values of mu less than 1. So that's understandable, it's rather nice. And the long wave analysis again delivers a diffusivity, but now the diffusivity is just depends on delta x. I can make it smaller by having smaller delta x. And before the diffusivity was delta x squared divided by delta t. I don't have that singular behavior now. The diffusivity is doesn't get bigger as delta t gets smaller. And here I've time stepped to 1, and the solution is only damped, it's a smaller amount of damping, is only damped down to 80%. That's not good, but it's not as bad as previous cases. Okay, so that's algorithm 3. Algorithm 4 is an implicit and second order scheme, the Crank-Nicholson scheme. And so we effectively central difference around the mid time level and at level n. So I'm going to work out the derivative. So I'm not doing upwinding, I'm allowed downwinding information. It's central differencing derivative from those 2 points and from those 2 points. And if I average the space central difference between there and there, I get the space time first derivative there. So that's this expression here. At time level n plus 1, I take the difference between that point and that point. At time level n, I take the difference between that point and that point. And then I time step by taking the difference between here and from time level n and time level n plus 1. And so this is central differencing around the midpoint. So this is central difference in space, central difference in time, second order in both. And but it's implicit. But for this linear equation, this very simple equation, that's not a problem. We can solve that. The stability analysis gives me an amplitude, and it's 1 minus I something divided by 1 plus I the same thing. So the magnitude of A is exactly 1. As the magnitude of A is exactly 1, whatever the parameters you put in, it has to be that the amplitude of your wave is unchanged. We're just propagating the wave sideways at the correct speed. Sorry. We're propagating the wave with preserving the amplitude. Remember, mu is the CFL condition, and sine theta that's this Fourier wave I put in. How much does the wave change over 1 delta x? It's k delta x. Okay. So it's actually stable for all values of delta t. It's unwise to use a large delta t because it's inaccurate and it will be moving at the wrong velocity. So the imaginary information in A, so A has a magnitude 1, but the theta, the imaginary, the ratio of the real and imaginary parts of A tell you how fast does it propagate, and it propagates at the wrong speed, considerably the wrong speed if delta t is wrong. So stability is great. We can do a long wave analysis to find out what the error is, and we find that there's no diffusion, which is good. So it is the correct advection, and then there's a delta x squared numerical, not diffusion. It's actually dispersion because it's got 3 derivatives. 3 derivatives mean that waves will propagate without changing their amplitude, but the speed that waves change depends on the wavelength. On the whole, long waves go fast, short waves go slow. And this is you can see this in the numerical solution. The amplitude is being nicely kept at 1, but the long wave is going at 1 speed, and there are some little short waves which are going slower, being left behind. So at the trailing edge, we see these little short waves, and we get these spurious oscillations. The original solution had no negative. The correct solution should have no negative values. Okay, so algorithm number 5. Here's the upwinding, and there's an expression for the numerical error. Artificial numerical diffusion. So think of that, remember that, there's a half 1 minus mu c delta x, is uxx. And what the Lax-Wendroff does is to take that expression and seize the uxx, and then we can work out numerically what uxx is. It's 2 spatial derivatives. It's the standard central difference of central differencing to get the second derivative numerically. So we then put that into this expression, rearrange everything, and get a formula here in terms of u at some position L at time level n plus 1 involves time level n before, it involves u at the same position L, and it involves L plus 1 L minus 1 and L minus 1. So we get a horrible complicated expression. The stability analysis is getting a little more difficult, and the answer is that simple expression after some work, and that is the magnitude of A will be less than 1 as long as mu is less than 1. It'll be less than 1 for all values of theta if mu is less than 1, which is what we expect. The long wave analysis is rather similar to the previous algorithm, and the numerical error is a delta x squared times a u with 3 space derivatives, u x x x. Okay, so we get numerical dispersion again, and it's slightly better. These wiggles are just a fraction smaller. So that's it's really holding time level 1, amplitude 1 very nicely. And this higher order, this second order method is introducing spurious oscillations because the slow waves travel slower than the main long wave. Short wavelengths travel slower than the fast long wave. Yes, yes. Yes? So you can, here we are, compare this last one, Lax Wendroff. You look at the picture, stare, record. I think this lobe here is a bit bigger because that's 1 here. So this, I reckon, is, well, that's 2 down to there. Is a third of the way down? Minutely different. Okay, the final one, algorithm 6. Nice, it's second order and it's explicit. But it uses 3 time levels. So we're going from now to the future, but we use 1 time step before. And the clever idea is to central difference the time derivative and central difference the space derivative around the open circle point. So at time level n, we're going to construct the time derivative, and we're going to, at time level n and at position L minus a half, central differencing on there. So for the time derivative, you can look at these expressions and see it as, it's an average. So we take the time derivative here, between there and there, and the time derivative between there and there, and we average the time those 2 time derivatives, so we get the time derivative at the open circle point. And then for the space derivative, that's easy. We can take the space derivative between those 2 to get it centrally differenced around the open point. So you put all of that in and rearrange, and you get this formula at the bottom that the answer up here is explicitly in terms of these 3 points. There's time level n minus 1, time level n, and then L and L minus 1. The stability criterion is much more complicated to get. You get a quadratic for A. Actually, it's best to say it's A times e to the I theta upon 2. Then you get this quadratic, and you can stare at that quadratic and decide very obviously it's stable to all values of theta as long as mu is less than 1. There's a challenge, if you like, complicated algebra. Derive this expression and then persuade yourself that A is less than 1 in magnitude, because it's complex, if mu is less than 1. What this quadratic for A is telling you, there are 2 solutions. There's obviously one solution that you'd like, and there's a spurious second solution, which will cause little problems. One solution will behave quite naturally as a mode which is traveling along, and the shorter waves will travel slower, so you'll leave a trail of things. But the spurious mode can travel in the wrong direction, or it can travel faster than and you can end up with short waves in front. Okay. If you look at the long wave analysis, where you're really picking out the main mode rather than the spurious mode, you find that we have an expression for the diffusivity, and now I think that diffusivity ought to be smaller. So it's not a diffusivity, it's a dispersion. It's a 3 derivatives. So it's the variation of the speed of waves, how the waves depend on the wavelength. So there's a solution. Now, will you buy that the wiggles are smaller? Amplitude being preserved as 1, and this one is sending out waves in front rather than behind. Sorry? Ah, well, right. So I can get rid of this effect by putting mu equal to 0.5 or 1. It's pretty obvious that if you have mu equals 0.1, 0.5, you're just propagating in one time step the information one half block to the side, and so it ought to work. If you come to this expression, I'm saying if mu is a half, this factor is 1, so that's gone away, and so the information here is exactly the information there. Okay, that's exactly true, and it would be useful if C were a constant. But of course, in practice, C's vary in space. They may vary with U, and therefore, it being exact for a special value of mu at one location, it's not true at another location. So it's a nice observation. You have to make it, but it's not helpful. Well, it's helpful that you made it, but it can't be exploited. Okay, so the conclusions for smooth data, if we were just propagating a nice smooth curve, it was 0, quadratically increases to a maximum. So it's continuous and has a continuous derivative. The general conclusions are there's this CFL parameter mu, and you want it less than 1. It's cropped up time and time again. You need this parameter less than 1. The odd order schemes, the first order schemes, and it's also true for third order and fourth order, they have some form of numerical diffusion, and the numerical diffusion spreads things out. And because they're spread out, the maximum amplitude comes down. Bad. The even order schemes, in general, unavoidably, and this is second order but also fourth order, they have preserved the amplitude, good, but they have short waves traveling on the whole slower than long waves, so you generate spurious oscillations. Okay, so we will find tomorrow morning, first lecture, these high order schemes are hopeless at discontinuous data, and you retreat to low order schemes. And then, given that information, of course, we can always do better. And what we do is we use the two of them. Near the discontinuity, we have low order. Away from the discontinuity, we have high order. And there's a technique of switching from one to the other. Okay?